We have seen many aspects here. Even though potential has a built-in ambiguity, so potential difference doesn't have any ambiguity. And we have seen in case of finite charge distribution, we choose infinity as a reference point, and we take potential at infinity 0. We choose potential at infinity 0, and these are the things that we have discussed, isn't it? And we have also discussed it for a spherical shell, okay? So on which charge uniformly spread over the surface. Potential inside is constant, and it should be, because if potential is constant, its gradient will be 0. That means electric field will be 0, isn't it? We have seen that one. Now let me get into again this mathematical part. Electric field is equal to minus negative gradient of potential. Am I right? Whatever the reference point we take, gradient will be same, isn't it? Field is unique, even though potential is not unique. I mean, that depends on the reference point. Electric field is always unique, isn't it? So now, so we shall take other two equations. Del dot E, that's equal to rho by epsilon naught. Okay. Del cross E is equal to 0, isn't it? Now, obviously, again, if you have this relation, again, you need to work out this part. This is obvious, am I right? We have already seen. Electric field is equal to negative gradient of potential. What does this say? This says curl of, if you substitute electric field, if I take negative sign outside, curl of gradient equal to 0, isn't it? This is not any, new statement. Is that okay? This is one of the vector calculus statement. Is that okay? So this will not give us any new equation, but this will generate a new equation. Now look at here. Del dot, what is E minus del V is equal to rho by epsilon naught. So this, if you take negative sign this side, it will be del dot gradient of V, that's equal to minus rho by epsilon naught. So this is equal to del square V is equal to minus rho by epsilon naught. So that means del square of V of R, okay, that's equal to minus rho of R divided by epsilon naught. We call this one as Poisson equation. This is a famous Poisson equation. Poisson's equation. Is that okay? So Laplacian of potential at any point in space, that's equal to minus of charge density at that point in space divided by epsilon naught. So this is actually a partial differential equation, isn't it? Poisson equation is actually a partial differential equation. Again, we can. I think mathematically we can find a general solution. Okay, by taking potential at infinity, we can find a solution for this one. So I think that is given in the appendix. Can you just check this out? Solution of this one can be found, I hope. Okay, it is given in the appendix. So check that out. Let me just see that one and let me interpret it. Is that okay? I mean, generalized solution by taking, so potential at infinity is equal to 0. Okay, that will become a kind of boundary condition. This is a partial differential equation. Am I right? Any differential equation, you need a boundary condition to solve that one. Okay. So for a finite charge distribution, if suppose rho of R not extending out to infinity, if it is localized, okay, in that case, I think we can find the generalized solution for this one by taking a boundary condition that potential at infinity equal to 0 or potential goes to 0 at infinity. Is that okay? So just check that out, appendix part. Okay, I think appendix B is saying some theorem. Check that out, appendix B. Now, if rho of R equal to 0 in space, okay, so again, so where again, suppose there is no charge in some space, okay, so if rho is equal to 0 in some places, is that okay? So then this will become del square V is equal to 0, am I right? This equation will become this kind of equation if rho equal to 0, isn't it? Are you getting fine? If you better write like this, V of R, isn't it? Is equal to 0. If suppose in some space, if there are no charges, okay, then again your potential will satisfy this equation. We call this as Laplace equation. Is that okay? We call it as Laplace equation. That's also partial differential equation that again, that can be solved. I think in the next chapter we are going to deal with this kind of problem. Is that okay? Solving Laplace equation. Now look at here. One question. Yes, speak out.
Sir, hello, sir.
Yes.
Sir, no charge means, in example, sir, no charge means.
No, you suppose here you have some charge distribution. So here you have some origin, okay? So here you are finding the potential, okay? Where there are no charge, okay? V of r. So if you find the potential here, del square V is equal to 0 here. Suppose here you have rho of r, okay? Here, suppose. So at that point, if you find the potential and if you find the Laplacian, so Laplacian is equal to minus rho by epsilon naught. That's what I'm saying. I mean, these are one-to-one correspondent. That's what I'm saying. Is that okay? Now look at here. Let me ask one silly question here. Laplace equation, am I right? Suppose I have two different charge distribution, okay? I will take some spatial point where there are no charges. I will have the same equation. I have two different charge distribution, okay? So distribution 1, distribution 2. Is that okay? And I will take point in space where there are no charges. I mean away from this charge distribution. I'll take a point away from the charge distribution where there are no charges in both cases. In both cases, same equation is followed, isn't it? Then in both cases, potential is same. Speak out. Are you getting a point? Suppose I have a spherical charge distribution here. I'm finding the potential here. Okay. So now I have some other planar charge distribution here. I'm finding the potential here. Is that okay? Now in both cases, this is the spatial point where there is no charge away from the charge distribution. So again, in both places, Laplace equation is valid, isn't it? The same equation is valid. Can I say potential is same? Speak out.
Sir, no, because
boundary conditions are different. Okay, even though this equation looks same for all situations, but here in this equation you have rho of r. Am I right? I mean, you may think that for different rho of r you will have different solution like that. But so this equation it is same for all empty space points. But boundary condition makes the solution different. Okay, we shall handle that one in the next chapter. So this part again, that's why the whole potential formalism is very rich actually. I mean mathematically it is very rich, and again it will also help us to solve very lengthy problem actually, where we may not able to apply Gauss law or Coulomb's law. The potential due to a localized charge distribution. Wait a second. Localized charge distribution. Localized charge distribution. Again, we have already done, again, in case of localized charge distribution, I told you can take your reference point at infinity, isn't it? We define V of r as some negative integral of infinity to r e bar dot dl bar. Am I right? But we don't, again, if we now electric field, why we go for finding the potential? Am I right? We need to find an alternate way to find potential, isn't it? Earlier, whatever the problem you have done in the yesterday's part, okay, you found electric field first. Am I right? Then you line integrate from infinity to some point and you found the potential, isn't it? But usually, so theoretically, that is not required. If you know the electric field, you can find the force, you know the dynamics of the system. Why do you go for potential again, isn't it? I mean, one thing is to have understanding of the potential, okay? I mean, even though it is meaningless, again, you will have understanding of the, how V of r varies, just like in case of spherical shell, isn't it? We found how potential is constant inside. And again, because of that fact, again, your electric field was zero, isn't it? This kind of idea is generated, okay? So, but we better to find the alternate way in case of localized charge distribution where we take a reference point at infinity, we better to find an alternative way. Now look at here, let me take a charge at what we call origin again. Charge at origin, let me find potential at a point R, okay, V of R. So can you quickly tell me, if you just find the electric field due to this one and if you line integrate, what would you get? Speak out. Speak out. Yeah, so electric field will be a Q by 4 pi epsilon naught R cap by R square. Am I right? If you line integrate and if you substitute the limit, you'll get potential at R due to a charge at origin. Okay, so that's equal to 1 by 4 pi epsilon naught, okay, Q by R. Is that okay? What is R? Distance of point of interest, point where you are finding the potential from charge. Am I right? So this is a distance from the charge, isn't it? Distance of the point where you are finding the potential from the charge. Now what I do is, I am going to what you call place charge somewhere else, somewhere here. I'll place charge Q here. I'll define R prime here. Is that okay? I'll define R here. I'll define R here. I'll define R here. And it's italic R. So now again, potential depends. This is a scalar, okay? Again, it has nothing to do with this R cap or something here, isn't it? That's why for this charge distribution, I mean charge, when you place charge other than the origin, or when you move the origin away from the charge, you can think like that. So potential at R, again potential at this point, again any point in space we refer to origin only. Is that okay? Potential at R in this situation, that we write like this: 1 by 4 pi epsilon naught Q by distance of this point from the charge, that is italic R, scalar. So this is my origin. This is my origin. Is that okay? Speak out. Where again italic R is the distance of the point of interest from the charge. Is that okay? But remember, this point, again mathematically we refer to origin only. Again, potential at this point, potential at R, that is the meaning. Okay, grab that idea. Now what I do is, I will place many charges here. I will place many charges here, many point charges here. Is that okay? So Q1, Q2, Q3. Is that okay? And so let me take this one as Qi. It is what you call Ri prime vector. Is that okay? So this is a point in space, R vector. This is italic Ri vector. Is that okay? So can I take like this? So there are many what you call Q4 like that. So there are many point charges here, source charges here. Again, this is the point where we are going to find the V. Is that okay? Now this is the scalar field. Am I right? Scalars add like a scalar. I mean, you can simply add. You don't have to consider any vector component and all. Am I right? So that's why potential at this point, I hope you know it again, we have already taken. It will follow what is that superposition principle. The net potential at this point, that's equal to potential due to charge 1 plus potential due to charge 2. So plus potential due to charge 3 plus and so on, isn't it? When you substitute those individual using this formula, what will happen? 1 by 4 pi epsilon naught, okay, Q1 by italic R1, okay, where Q1 is the first charge, italic R1 is the what you call distance of first charge from this point, okay. So plus Q2 divided by italic R2 plus Q3 divided by italic R3 plus and so on. Check this out. Superposition principle allow us to find this one. Now it's a scalar addition. There is no vector at all. Okay. So that's why the what you call potential formalism is more easier to handle. Later again you take the gradient, you find the electric field. Is that okay? So that's the basic idea. Now look at here. Let me move on. So can I write like this? So 1 by 4 pi epsilon naught, okay, summation over I, Qi divided by italic Ri, in a summation convention. Remember, this whole thing works only for localized charge distribution, this has an inbuilt assumption that potential at infinity vanishes, okay? This whole thing, whatever we are writing. For infinite charge distribution, you can't deal like this. Is that okay? You can't take infinity as a reference point, okay, in other sense, okay? Be careful. Now, what I do is, I will take a, what you call, continuous charge distribution here. I'll take origin, okay? I'll take some continuous charge distribution, that may be line charge, volume charge or something, okay? Then what we do, we define dq, am I right? And we are going to find its distance from the origin, r, italic r, isn't it? So we wish to find potential at this point. And in that case, again, we can just generalize this one. This was a summation. Now we can generalize this one to integration 1 by 4 phi epsilon naught, okay? Integral of dq divided by italic r. Is that okay? Integral of dq divided by italic r. Check this out. So, I mean that this may be volume charge distribution, we shall take care now. Is that okay? Suppose if it is a volume charge distribution, then what will happen? Can you just edit that one? Again, now look at here. This integral is a scalar integral. Earlier, in case of electric field integral, we had r cap by r square, am I right? That was quite difficult to handle. Now it's a scalar integral, look at this one. Now again, let me take volume charge distribution here, okay? Let me take a volume charge distribution here, and let me define one infinitesimal volume element here. Is that okay? At a distance r prime, so from the origin, is that okay? And let me take one more point in space r, where I wish to find the potential, is that okay? And this is italic r vector, and this is d tau prime. This is d tau prime. So then what we do is, we define rho of r prime, am I right? Pick out. So in this region of the, what you call, source charge, we define charge density, am I right, in case of volume charge distribution. So in that case, we can write our potential at r. So that's equal to 1 by 4 phi epsilon naught. How can we write dq? Rho of r I can write as dq by d tau prime, am I right? So that's why dq I can write as rho d tau prime. Isn't it? Speak out. Are you grabbing this point? Very simple. So dq I can write as rho of r prime, so d tau prime. So I can just do that one, isn't it? So rho of r prime, d tau prime, that was equal to dq divided by italic r. Again, it's a one more scalar integral. Is that okay? Speak out. Suppose if you have what you call, if you have surface charge distribution, suppose you have a surface here, okay, where you define a sigma of r prime. So where you define a small patch of area, okay, dA prime at a distance r prime from the origin, and this is the point where I wish to find the potential, okay. So now this is italic r, and you will define sigma of r prime, okay, surface charge distribution, that may be function of r prime. We have taken this idea, isn't it? So then dq, so what you call the charge, so this was dq, okay, we have substituted that one. Charge of this patch of area dq is equal to sigma of r prime into dA prime, and we can write the potential due to what you call surface charge distribution 1 by 4 phi epsilon naught. Check this out, sigma of r prime dA prime divided by italic r. Am I right? Surface charge distribution.
Sir, here you wrote, sir, rho r prime, sir.
Rho of
R prime, sir, r prime, sir. So volume charge density will be the function of r prime.
Yeah, in the most general case, volume charge density may be different at different points. Why do you take a special case? Take a generalized case. We have taken many problems again earlier, wherever what you call, we have a sphere, we have volume charge distribution in a sphere, which is a function of radial distance and all. Am I right? There are many problems, Vasla problem, like that. Volume charge distribution may be a function, okay, function of what you call this one, r prime. Why not? I mean, when you move at different point, you may have different charge density, isn't it? Are you getting point in that region?
But for infinitesimal purposes, it is different, sir. But if we consider the whole case, sir, then it is a function of rho r prime, sir.
Yeah, obviously. I mean, first try to understand what is density. Density is a point function, am I right? It's a scalar function, isn't it? That density can be different at different points. That's what I have written here, rho of r prime. And this integral is with respect to r prime. That's why we put prime here. I think we have taken the same idea in case of electric field, isn't it? That means you need to integrate r prime. This is a fixed point. R is fixed here. You will integrate here, okay, with respect to r prime. That means you are sweeping all over the region of the source charge. And at different point, you may have different density. So try to grab the idea about density properly. Is that okay? Speak out.
Yes, sir. Yes.
And this prime, because we need to integrate again, in that integration variable is this r prime. Is that okay? Suppose after finding this potential, suppose if you want to find electric field at that r, okay, what you do? You are going to do negative gradient of v of r. Am I right? Now this gradient, this derivative is with respect to this one, this variable. So find the difference. This is x comma y comma z, or this variable. Am I right? R, x comma y comma z. Am I right? This is x dash y dash z dash, isn't it? This one is x dash y dash z dash. Am I right? That's why we have written r prime. Now integral is with respect to this one because we need to sweep the region of the what you call this continuous charge distribution. But later, if you want to find what you call, you found potential here. If you want to find electric field here, you need to take gradient of the potential. While taking the gradient, what you call, you have to what you call take the derivative with respect to coordinate of this point. Is that okay? This gradient contains dou by dou x, dou by dou y, dou by dou z. So this d tau contains dx prime, dy prime, dz prime. That's the difference, okay? So find that one. Find that small, what you call, difference here, okay? So similarly, in case of line charge distribution, I hope you can deal with this one. Remember, this whole thing works for finite charge distribution. Don't take infinite plane. Don't take infinite line charge. This whole thing works only for finite charge distribution, okay? Let me take a line charge, okay? So in that one, let me take a small, what you call, dl prime. It is at a distance r prime from the origin. This is the point where we wish to find the potential. Italic r. Is that okay? This is dq. And what you can do, you can define lambda of r prime, am I right? Line charge density, isn't it? And dq, you can write as lambda of r prime into dl prime, isn't it? Charge per unit length. So that potential at r, you can write like this, isn't it? Potential at r due to this one, v of r is equal to 1 by 4 pi epsilon naught integral of, okay, lambda r prime dl prime, that is equal to dq, okay, divided by italic r. And again, this whole thing is for finite charge distribution. Don't apply this formula for infinite wire, okay?
Why?
That's what I'm saying. Again, it is for finite charge distribution. We have taken infinity as a reference point. I've taken yesterday one example of infinite plane. If you take infinity as the reference point, your potential itself will become infinite, isn't it?
So, sir, it will diverge.
Again, you can't what you call define the potential, but again of what you call infinite charge distribution by taking infinity as a reference point. Okay? You can do that one only for finite charge distribution. So this has an inbuilt assumption v at infinity vanishes, okay? Speak out, or our reference point is equal to infinity. So that is the inbuilt assumption behind all of these, okay? That's why this can be applied only for finite charge distribution. So take the example of yesterday's one. I have a what you call sphere, okay? I'll choose what you call center of the sphere as the origin. And I want to find the potential at a distance z along z axis, okay? This is x axis, y axis, z axis, okay? And I want to find potential at a distance z. This is the distance z from the origin, okay? Origin, not reference point, okay? O. And you have uniform surface charge, okay? Not volume charge, uniform surface charge, okay? Spherical shell of thickness almost 0, you can take like that. you need to find potential at this point, okay, V of Z. Using this formula, whatever the formula we have generated now, okay, for continuous charge distribution, we need to find this one. Again, this Q is uniformly spread over the surface, okay. You can define sigma, isn't it? Sigma is constant if it is uniformly spread. That's equal to Q by 4 pi r square. Let me take capital R as the radius of the sphere. Speak out. Charge per area. 4 pi r square is the area? Yes. Now look at here. Again, to find the potential V of Z, look at here, we need to apply like this 1 by 4 pi epsilon naught, okay? Integral of dq divided by r, am I right? So that dq we have to write like this 1 by 4 pi epsilon naught integral of sigma of r prime, but that's constant, okay? Sigma is constant actually. It will not vary. So dA prime, okay, divided by italic r, isn't it? That means we need to take a small patch of area here, isn't it? So shall I assume like this? It's a small patch of area. Is that okay? Small patch of area here. I'll call it as a dA prime. What is the distance of this? This is on the surface, okay? Can you just imagine? This is on the surface here. So now, what you call, again, what is the distance of this one from the origin? That is, again, that you have to take it as r prime vector actually. This one you have to take r prime vector, isn't it? But that r prime vector is equal to r. Again, that magnitude is r itself, am I right? Speak out. R prime vector, but magnitude of r prime is equal to r itself, remember. Is that okay? And this is your, what you call, so small r vector, okay, that small r vector I can write like this, am I right? That's equal to z into z cap. I know that one, modulus is z actually. Now your italic r, this is the point of interest from the source dq, okay. So can I write like this d a prime and dq corresponds to this one. So this is the italic r. Speak out. This is the italic r. So using some vector, what do you call, algebra, can you define italic r? That's equal to r minus, r minus r prime. We already know that one, am I right? Speak out. Now look at here. Again, to define this one, look at here. I need this italic r, am I right? Magnitude of this italic r. That's why let me define square of this one. Speak out. Square of this one. That's equal to r square plus r prime square minus 2 r dot r prime. Speak out. What is r dot r prime? Look at here. This is r prime. What is this angle? According to our polar coordinate, that is theta. Speak out. Am I right or not? So go for spherical polar coordinate. This is a radial distance. Then this will be theta. Am I right? Angle of what you call this one. What you call with respect to z axis. That you define that one as a theta, isn't it? Speak out. So this is equal to r square. That what do you mean by this r square? That means it is equal to z square. I know this magnitude. Z square. What is r prime? R square minus 2 r dot r prime. That is equal to z into r. Okay. Into cos of the angle between them, cos theta, and I got magnitude of italic r. I got this one. You have to take the root of this one. Is that okay? Speak out. Then anyway, over the surface, this is constant. You can take it outside the integral, isn't it? Sigma, that's equal to this one. You can take it outside the integral, divided by 4 pi epsilon naught. Integral of what is dA? What is this dA? This is a surface area, what you call, that patch is perpendicular to r cap vector, am I right? Speak out. That's actually dAr, whatever we have written dA prime, that's equal to dAr. Is that okay? That's a surface area perpendicular to r cap actually, on the surface. Can you just remind me that one? So that's why that dAr, what was that dAr? Speak out. H theta, H phi, d theta, d phi. Speak out. Divide by italic r. And one more, wait a second, you better to change the convention. So actually, this is prime, am I right? R prime, R cap prime. I better to take all prime because you have to do you should know with respect to what you are integrating. That's why you better to, so what you call, make this one as a prime. You take it as theta prime also. You take theta prime, H prime, phi prime. Here also you take theta prime because you should know that you are integrating with respect to source charges here. Okay. So because again, we will have some ambiguity here. Again, while integrating, don't think that okay, R prime is variable. R prime will sweep throughout this one, not R. Is that okay? Whenever we think about spherical polar coordinate, we write R theta phi, am I right? But here our R is different. You might write R prime, theta prime, phi prime here. But R prime is constant, that's equal to capital R here. R theta prime, phi prime. Are you getting fine? So this is what we need to integrate here. Is that okay? That integration, again, whatever the R prime we have written, this is R prime, theta prime, phi prime. You better write like this. Your spherical polar coordinate. To run this integral, whatever the spherical polar coordinate you choose, put a prime over there because it's not, if you write R theta phi, again, you may end up with trouble with this R. This R is not variable. You are not integrating with respect to this R. Be careful. Is that okay? That's why I put theta prime here because we have already taken R prime here. R prime is variable. We need to convert this position, R prime, this position in space with again into what you call spherical, so polar coordinate. And this R prime is variable. That's why again, so write everything as a prime here so that there is no more confusion. Is that okay? DAR prime. So that's why that's equal to sigma by 4 phi epsilon naught, okay? Because we have taken one more R here. That's why we need to avoid the confusion. Is that okay? If we have taken this one as something else, so that was okay. But so point of interest from the origin, that is R, am I right? That we are not integrating with respect to that R. We are integrating with respect to other R. That's why you need to change, okay? Look at here. What is this one? R square sin theta prime d theta prime d phi prime, okay, divided by italic R root of z square plus R square minus 2 zr cos theta prime. So that d phi, again, what is this? This is R prime square again. No mistakes allowed here, okay? R prime square, is that okay? Speak out. This one, not this one. Look at here. If I have written R square, look at here. I would have written Z square there. No, that's not Z square. That's R square. Are you getting point? That's why again. So change the what you call convention here, and you should know which is variable. Is that okay? So this R prime square is capital R square again. Yeah, speak out.
Sir, I'm not getting the area part, sir. I mean, how do you take this area, sir?
Again, if you take any patch of area here, so that is radially outward, DAR. How you have written DAR? Speak out. H theta, H phi, D theta, D phi, R cap. But you don't have to take what you call that vector part. You have to take only scalar part. Speak out.
Okay.
That's what I have taken, the H theta.
Yes, sir.
But only scalar. I don't have to take R cap. Here there is no vector things will come, isn't it? Scalar part. Is that okay? That's what I have done. So anywhere you will take it is radially outward, am I right? That part of the dA vector that I have taken. Is that okay? Let me rub out this one. Need to save some space. Okay. So that's why potential at Z is equal to, look at here. So that sigma, this R prime is capital R because wherever you go over the surface, the distance from the origin is a radius, am I right? Sigma and integral of d phi, that's equal to 2 phi. So 2 phi R square, okay, divided by 4 phi epsilon naught. This will come outside. Integral 0 to pi, am I right? Theta prime will run from 0 to pi. Sin theta prime d theta prime whole divided by root of z square plus R square minus 2 zr cos theta prime. You can substitute. You can do integration by substitution, am I right? You can substitute this one as some t When you take cos theta derivative, you will get sin theta d theta. 1 by root t, derivative is 2 root t, like that, isn't it? Sorry, integral. And you can do that integral. Let me substitute that one directly. Is that okay? Let me do that one directly. Do this one. Substitute denominator again inside the square root, substitute as t and do the integral. You will end up with this one. Here comes one what you call tricky step, okay? Here comes one tricky step. Wait a second. Sigma 1 the 2 the, am I right? Sigma r square divided by 2 epsilon naught, okay? So this answer is 1 by rz, I think. 1 by rz root of r square plus z square minus 2rz cos theta prime, okay, where theta prime runs from 0 to pi. Where theta prime runs from 0 to pi. If you substitute the limit, okay, be careful while substituting the limit. I think, yeah, when you substitute the limit, what will happen is v at z is equal to sigma r square divided by 2 epsilon naught. Yeah, speak out. Any problem? 2 epsilon naught. 2 epsilon naught. 1 by rz, okay, 1 by rz, upper limit, okay, upper limit, cos phi is minus 1, am I right? This will become r plus z the whole square, root of r square plus z square plus 2rz, okay, upper limit, minus lower limit, root of r square plus z square minus 2rz, okay. So now look at the small manipulation. Try to what you call grab some logic behind this one. Sigma r divided by 2 epsilon naught z, okay. We write this one as root of r plus z the whole square minus root of r minus z the whole square. Am I right? Check this out. Now one thing that you need to what you call take care here, you have taken the root of some quantity, am I right? Root of some positive quantity. This cannot be negative quantity. So now here you have one choice. You can write it as r minus z the whole square or z minus r the whole square. You have this problem later, okay? You will end up with this mathematical problem later in some further chapter, okay? Which is higher? Z is higher or r is higher? Speak out. Z is higher or r is higher? Speak out.
Sir, in this case,
Z is higher, am I right? So that's why a root of r minus z the whole square. If you write that one as r minus z, that would be negative, am I right? Speak out.
I think critics right, Z minus right.
Yeah, that's what I'm saying. What I'm saying is, look at here, root of r minus z the whole square, okay? This whole thing should be positive, am I right? Root of some positive quantity. Suppose if you take root and if you write r minus z, what is r minus z? Negative. That should not happen. Are you getting the point? Be careful here because root of, this is positive quantity, you know square, am I right? Root of some positive quantity, how it can be negative? So that's why you write r minus z the whole square as z minus r the whole square here. Is that okay? Then it would be correct. So that sigma r by 2 epsilon naught z, okay? So this is equal to r plus z the whole square under root r plus z, okay? Minus z, again, so minus of z minus r. Is that okay? So z will get cancelled, r will what you call add up, sigma r square by 2 epsilon naught into z. Check this out. Sigma r square divided by 2 epsilon naught into z. What is the mistake? 2r will come, 2 will get cancelled. Speak out. So potential at z is equal to sigma r square divided by epsilon naught into z. Are you grabbing my point? Why I have written r minus, again it looks like, again you can write z minus r the whole square but or r minus z the whole square, but You have taken square root of some positive quantity that cannot be negative. Okay, be careful in that one and manipulate that one. Okay, so Z is greater than R. Okay, Z minus R is positive. Take that idea. So now substitute sigma. What is sigma? Q by 4 phi R square into R square divided by epsilon naught into Z, isn't it? R square got cancelled. This is equal to 1 by 4 phi epsilon naught Q by Z. We have already found this result, am I right, earlier, yesterday, by line integrating electric field, potential at some point outside the, spherical shell. We already found where Z is the distance from the origin, isn't it? We got R over there. Now R is nothing but magnitude of R is nothing but Z here. We got that one. But look at the, effort that we have done here. We put more effort, okay? We put more effort here, isn't it? While integrating. Spherical integral, it was quite, we needed to put some effort here, isn't it? That you need to have experience here. Because which method to choose, isn't it? That's very important. Speak out, is that okay? This was little bit difficult than yesterday's one, line integrating this one, am I right? Again, you know what is the electric field outside? Outside of this one, 1 by 4 phi epsilon naught. So Q by R square R cap, am I right? So then you can line integrate from infinity to this R, E bar dot dl bar, so 2-point potential at R, isn't it? Then you put R equal to Z, that's it, isn't it? You could have done that one. That was more easy. Because we know, according to Gauss law, this would be electric field, isn't it? Gauss law would have helped us to find electric field, and from electric field you can find the potential. But here you find directly the potential using this one, 1 by 4 phi epsilon naught integral of dq divided by italic R. That was more difficult actually. Is that okay? Because spherical integral, isn't it? No, again, mathematically, when you look at the last expression, this potential is equivalent to the potential due to a charge at the origin, total charge Q at the origin, isn't it? That's mathematically equivalent to like that, okay? That happened like that. I can't answer why, I think, okay? Why sphere behaves like a charge which is point charge, am I right? When you see this potential, so V at Z is equal to 1 by 4 phi epsilon naught, am I right? Q by Z, am I right? Speak out. Q by Z. Now, again, it looks like, if whole these charges concentrated at the origin, you would have got the same potential, am I right? So, whatever the potential you got outside, okay, so that is equivalent outside, okay, inside potential is constant, inside the same thing will not happen, okay. This is equivalent if total charge is situated here and you are at a point Z from the origin, isn't it? Again, you get the same potential in both cases, am I right? But inside potential is constant here potential is variable everywhere, be careful. But outside the sphere, your potential happened to be like that. Again, it happened like that, I don't know why. Is that okay? So think over it.
Sir, Z is very large distance from that sphere.
No, not even large distance. For a finite distance also the same is true. We haven't taken any approximation that Z is large. Even for a finite distance from the origin, outside the sphere, electric field as well as potential, it looks like electric field or potential due to a point charge at the origin, isn't it? We have seen that one.
Sir, what will happen if Z will be very high? It will be...
No, then also, again, whatever the Z you take, again, if you go to infinity, it will be 0. You can take, it is in the denominator. If you go to infinity, it is 0. Even though Z is very high, again, you will have the same. Again, here we haven't taken any approximation. There is only one Z, isn't it? There is only one variable, Q by Z, only one variable. You don't have to approximate anything. Is that okay? Even though Z is high, the same relation is true. Potential keep on decreasing, that's it.
There is no potential, right?
If you go to infinity, there is no potential. How far you are, that does matter, am I right? If you go to infinity, 1 by infinity is 0, obviously. Again, that's what we have already taken. Infinity as a reference point, infinity as a zero potential, that we have taken as a kind of boundary condition. Obviously, that should happen. Our answer should follow that one. When you go to infinity, your potential should be zero. Otherwise, it would be wrong. Is that okay? Speak out. Because we have taken infinity as a reference point, infinity as a what you call zero potential. Obviously, that should happen after you find that one. Is that okay? Speak out. Now, finding the potential.
Always,
Speak out.
that's why we always take that infinity reference point.
Not always, only for finite charge distribution. For finite charge distribution, we always take infinity as a reference point. For finite charge distribution, we set infinity as a zero potential, and that will happen even after we find that one. Obviously, that should happen. Is that okay? It's a kind of boundary condition actually, if you see the differential equation, okay? Finding the potential. Okay? So you have two ways, am I right? Today we have done one. Suppose if you have a rod where you have a uniform line charge, okay? Suppose you have two charges, okay? Two charges, Q1, Q2, plus plus Q plus Q. Suppose you have two charges. Suppose I want to find the potential at a distance z from the midpoint of these two charges, okay? This is the midpoint. So if I want to find the potential here, what you need to find? You need to find this distance, you need to find this distance, am I right? Let me write R1, R2. You have to find 1 by 4 pi epsilon naught, okay? So Q by R1 plus Q by R2, speak out. So or Q1, Q2 here, Q1, Q2 here. No need to write any vectors, am I right? It will add like a scalar. It's very, very simple. Finding the potential, okay, is very simple because it will add like a scalar. So that's why, again, there are some advantages of this potential formalism. Again, suppose if you want to find potential at this point z, if you take what you call this one, I think, so this is dq, isn't it? This is italic r, x or something. We have taken like that, am I right? Now look at here. Again, you are going to do dq by r, where dq is equal to lambda into what you call dq is equal to lambda into dx like that. Am I right? We have done that one. Now again, this is a scalar integral. This is much more easy than our vector integral in case of electric field. In case of electric field, we needed to find the what you call electric field here. We need to split that one horizontal component, vertical component here, isn't it? We vector addition, am I right? We need to take care about component and then we need to add, isn't it? Speak out. But here nothing. You just find the what you call scalar distance from this point of charge to the point of interest, and you just integrate. So that's why this has its own what you call advantage. Okay, observe that one properly. Yeah, speak out.
So after we are calculating potential and then we take gradient.
Gradient, you will get.
Same reference point as
You should. Now look at here. Take all problem, whatever we did before Gauss law, after Coulomb's law, before Gauss law. Is that okay? For a Gauss law problem as well as what you call your what is that? That again in case after Coulomb's law we have done this rod problem, disk problem, like that. Do you remember? Ring problem. So now find the potential using this formula. Okay, integral of dq by r. Okay, find the potential using this formula. Take the gradient and check out whether you get the same answer or not. Is that okay? That kind of problem I think exists in Griffiths. Okay, he will give that kind of problem. Not what you call Gauss law problem. Take earlier problem. In case of rod, finite rod, we can't apply Gauss law. It's not a symmetry. Am I right? So in case of what you call what else you have taken? Rod and ring and disk. Am I right? So again, ring is also not any symmetry, isn't it? Again, disk is also not any symmetry. Am I right? I mean, disk has some what you call cylindrical symmetry, but again, we don't take it as a cylindrical symmetry. Okay, we take wire, infinitely extended wire or infinitely extended cylinder as a cylindrical symmetry. So again, for those three, you find the potential using this one, okay? So then so take the negative gradient and check out how you get. Obviously, let me give you the hint, okay? Let me give you the hint. In case of rod, okay, what will happen is, or let me take this one. I hope in case of this one, this is constant, okay? Only this z is variable, okay? V, you will have a function of z. When you take a gradient, what will happen is only z cap will appear actually. You will have electric field along z cap, okay? You will have that experience. Do that problem. Is that okay? Do that problem. Speak out. Finding the potential. There are two ways, am I right? One is, this is for exam, okay? It's for exam, not, theoretically, again, we have done that one. Yeah, anyway. So, potential at R, that's equal to integral of some reference point to R E bar dot dl bar. Am I right? This is one way of defining the potential. Other one, for finite charge distribution only. For finite charge distribution, you can write potential at R is equal to 1 by 4 phi epsilon naught, okay? Integral of dq divided by italic R. This cannot be applied for infinite charge distribution, but this can be applied for finite charge distribution or infinite charge distribution. For finite charge distribution, you have taken, again, so write down, O taken as infinity for finite charge distribution. Okay, O is some finite point in space, whatever you choose, okay? For infinite charge distribution. I hope if you have solved yesterday's problem, I think you might have experienced this one, am I right? Speak out. Yesterday's problem was like that only, am I right? Integrating electric field only, 2.21 to 2.204. Speak out.
Yes, sir.
You might have experienced that one. For infinite line charge, you can't take infinity as a reference point, okay? Now look at here. Again, we have two cases. When we need to use this one, when we need to use this one, isn't it? We need to use this one when electric field is very easy to find. Is that okay? If Gauss law, we need to use this one if Gauss law allows us to. This for exam, okay? Find electric field easily. Gauss law helps us to. Gauss law, yeah, allows us to. Yeah, that's correct, okay? If Gauss law, if there is a symmetry, planar symmetry, cylindrical symmetry, spherical symmetry, then we can quickly find the electric field using Gauss law. And it's very better to line integrate that electric field from infinity to that R, if it is finite charge, or some reference point to that R, and quickly find the potential. Is that okay? So, if Gauss law is not helping to find what you call electric field, okay? Is not helpful. Suppose in case of rod, in case of disc, okay? If Gauss law is not helpful, that means if you need to find electric field like this, 1 by 4 phi epsilon naught integral of dq divided by r square into r cap, am I right? If Gauss law is not helpful and we need to find this electric field, then don't go for finding this electric field, go for finding the potential. Look at these two integrals. You find the electric field, then you go for this line integral to find the potential. That is meaningless. You directly do this integral. This integral is more easier than this integral.
Sir?
Finding the potential is a target. Wait a second. Finding the potential is a target. Is that okay? If Gauss law is not helpful, if you need to find electric field by this kind of integral, just like in case of disk, in case of wire, in case of what you call ring, isn't it? So in case of finite wire, okay, in case of finite rod, you found electric field by this formula. Then again line integrating, you will get what you call the same potential, but that is not meaningful step because that's a lengthy step, isn't it? You directly apply this one. If Gauss law allows us to find the electric field easily, then use this one. Find the electric field first quickly using Gauss law, line integrate that one, find the potential. Okay. If it is infinite charge distribution, usually they will ask a potential difference. You will find that kind of problem. Okay. Because again, there will be ambiguity in the reference point, isn't it? If you take infinite charge distribution, anyway, you can work it out. But this is only for finite charge distribution. This cannot be applied for infinite charge distribution. Usually infinite charge distribution is infinite wire, infinite plane. These two we have taken, am I right? Or infinite slab, infinite cylinder. Those all had symmetry and our Gauss law allowed us to find the electric field, okay? Speak out. So solve all problem in all different way, then you will understand, which method to follow. Yeah, speak out. You're asking something?
Sir, can we say that for continuous charge distribution, we can use this one and for
No. Again, we may deal with continuous charge distribution only. For discrete charge distribution, obviously this is easy, am I right? Not integral, it will be a summation. Is that okay? But I'm talking about continuous charge distribution only. Now, write down the example. What are the example? Rod, disc, okay, and your ring. This kind of problem here. Is that okay? You directly apply this one. Don't go for this one and then doing the line integral. Okay. What is the example here? Spherical symmetry, sphere, either solid sphere, spherical shell or something. Am I right? Infinite plane, infinite wire, infinite cylinder. Sphere is finite charge distribution. These are infinite charge distribution. For this one, usually infinity as a reference point. Am I right? While dealing with a sphere, take infinity as a reference point. While dealing with infinite plane or infinite wire, take some finite point in space as a reference point. Is that okay? But initially you solve in both ways, then later try to understand. This is the best way. Okay. Now you can start solving example number 2.25. I will solve example number 2.26. Leave that one because it's quite tricky. You can try that one. If you couldn't get, you can leave that one. But I will mention that one in the homework. Okay, you don't worry. You can submit the homework. I think 2.25, it contains 3 problems. You need to do that one. Along with outside the chapter, quickly note down. You can start solving. Outside the chapter, you will be able to solve problem number 2.49, 2.50, 2.52. This 2.50 is odd question. 2.52, this problem is required to solve some odd question. Problem number 2.49. Is that okay? Problem number 2.49, 2.50, 2.52. Quickly. Note down. And problem number 2.25, there are 3 problems in that one. Okay? Do all of this. For solid sphere, again, he might have use this expression to find potential inside and all. Okay, but I think that integral may be quite lengthy. You can try that integral. Okay, if that integral is lengthy, because for a sphere, spherical symmetry, Gauss law will allow us to find the electric field. For exam's sake, we can do this one.